So as I was saying, up next we have really fascinating. I'm really this looks really exciting, especially from this beautiful picture. Wow, look at that. So I'm going to also introduce Tom first because he's in absentia. Tom Reichert, who is presenting, would have been presenting today, but unfortunately can't be with us today because he's sick. Studied theoretical physics at the University of Frankfurt, and is now a postdoc at the Frankfurt Institute for Advanced Studies. He's also a fellow at the SPTG in Frankfurt, which for the non-German speakers among you might be difficult. Stiftung Polytechnische Gesellschaft, which is one of those lovely long compound words. But he's also and has actively been communicating in science and podcasts, exhibitions, public source, as all good science communicators do. And of course, with us in the flesh is Sascha Vogel, an old hand in the world of science communication and outreach in Germany. He's the founder of Science Birds, which you might say something to us about. And he also holds a PhD in theoretical physics from the University of Frankfurt. Without further ado, I will hand over to Sascha the concept of warp space from a physical perspective. Thank you so much.
Hey, thank you. So again, as has been mentioned, I'm replacing Tom for today, and I learned that yesterday evening. So I talked a lot about time travel and so on, so I knew the topic, but I hacked together a couple of slides, so bear with me. So what are we going to talk about? As you mentioned, there we go, the concept of warp from a physics perspective, or just to make it a bit more appealing, why time travel doesn't work and how to do it anyway. So this is the real physics talk, and again, as for the people who mentioned or have been here earlier, a couple of pictures have been generated with AI. The rest has been blatantly stolen. So I tell you, if you need the sources, etc., please contact me. I just didn't have the time to put that on. Again, yesterday evening. What's warp? And I found a very beautiful quote online. So think less scary alternate universe and more full-on psychedelic spiritual Lovecraftian mindfuck. Excuse the language. That is a commenter from Reddit. So, but what is the? But this is not canon. So this is basically online. Why are we talking about? What do we need the warp for in Warhammer 40k? We mostly need it for faster than light travel. It's basically the reason why we need it from a story point of view is we need to go from here to there much faster than the speed of light. So why do we need that? And again, this is from the presentation I gave earlier. The speed of light is 300,000 kilometers per second. So just to give you some idea, how long does it need to go from here, the Earth, to someplace else? 1 second to the moon, 8 minutes to the sun. Everything's rounded here. Roughly 4 hours to the farthest planet in our solar system. If you want to go to the next star, it's like 4 years. And of course, we need to get the next galaxy as well. Then we are in the range of a couple of million years. That is a problem. So obviously, you can talk, and again, there are a couple of sources that, yeah, you have generations and they replicate on the ships and blah, blah, blah. But still, we only have 40,000 years. So that's the name of the game, basically. So within 40,000 years, we just won't make it there, even with the speed of light. That's a problem. So we need, just from a story point of view, we need faster than light travel. So now I'll tell you why it is impossible. And then the rest of the talk I spent on why or how to do it anyway. So why is faster than light travel impossible from a physics point of view? Are there any physicists, any natural scientists in here? Anybody who has seen, anybody who has seen a Minkowski diagram somewhere? Okay, good. So a couple of no, a couple don't. This is basically the problem. So you have like two cones. The one going up is to the future, the one going down is to the past. So the axis top to bottom is basically the flow of time. So the blue lines are the speed of light. So this is basically the fastest you can go. If you are faster, you're actually in this region here. You're basically faster, so you make more space in less time, which is far. So this is impossible because the speed of light, from a physics point of view, is the fastest we can go. There's the theory of relativity and so on and so on. And there are a lot of people, the crackpots, we call them, who claim, oh, we have like faster than light travel, we invented this, we invented that, for like 120 years. Nobody has ever found anything. And trust me, we tried. We seriously tried. There is no way around that. And it has been measured to, I think now we are at the 16th digit or something. Every precise measurement we have, there is no faster than light travel. And even if you find something which is faster than light, it's like a meter per second faster. So given the accuracy we have right now. So this is like, if you trust in one thing in physics, trust in this. So this is a problem, because it tells you there is no faster than light travel. And even if you have like a second event, as you call them somewhere else, you never can reach the other areas because they all go in parallel. You cannot never intersect the lines. So that's a problem. This is one thing we hold dearly in physics is causality. Everything we do or everything that happens has what in English? Cause. Yeah, thank you, causality. So everything that happens needs to have a cause, and that needs to be timeline. As we're going back, so you cannot have something happening here having an effect there. There is just cannot happen. So causality is a problem which you have to address. So the error of time, because there might be a way around time travel after all. Who tells you that time is flowing in this direction rather than this direction? But going back to this one, who tells you that this is a past and this is a future? Maybe we can just reverse the arrow of time and at least go back in time. Why does it not work? Here's a video. I'll just show you. There you go. It's a standard billiard game until you realize it's actually going the other way around. In classical mechanics, in classical physics, nobody is telling you that time is going in this direction rather than in this direction. Physics doesn't care. Even everything about this is physically absolutely correct. So why not? Why not go back in time? The reason is pretty much this, which is the second law of thermodynamics, which is your main enemy in the universe, which tells you that entropy always has to be, or the change in entropy always has to be greater than zero. So entropy grows. And there's always the way people explain entropy is like it's an order for chaos. It's a measure for something not ordered, which is physically, excuse my French, it's bullshit. But for what we plan today, it's good enough. So entropy is basically, in a very simple way explained, just imagine you have like an aquarium. You have a yellow liquid over here, a blue liquid over here, and a glass door in the middle. Now you remove the glass sheet, what happens? The two fluids mix, right? Yellow plus blue gives green, everybody's happy. The entropy increased. So we call it the phase space. So basically, the place where particles can be at what state basically increased. So the yellow stuff can now be over here, blue over here, they mix, you have green liquid. Fine. There is no way, because of this, that one green aquarium suddenly gives you a yellow one and a blue. It just doesn't happen. That's because entropy always increases. So this is good because it tells you time has a direction. Time goes in the direction of greater entropy. So fine, which is like a thermodynamic argument. So basically from an adjacent field, you have to combine those two. But is there a way to actually just from physics, from one field itself to actually find an error of time. And yes, there is. How can you check that? And I give you the second equation of the talk, which is this, which you will not understand if you didn't study physics. It is, I would argue, the most important equation in all of physics. It's the Euler-Lagrange equation. Again, everything you need to know about physics is in this L. So everything you have in physics, don't try to understand me wrong. We can talk in the break, happy to do so. But the point I want to make here is the L is basically all your theory. Everything you need in your theory, you have to take in that L. It's a huge formula. Put all the symmetries you want, all the interactions you want, everything you want the world to do from a theoretical point of view, you put in that L. Then you plug it in this equation, calculate, and it gives you what we call the equations of motion. The way the particles or fields, whatever you need, behave. It's like a just simple mathematical procedure. Straightforward. There is no left or right. There's just straightforward, just calculate. So what you can do in the L, you can basically replace plus time with minus time. You can do that. Just wherever there's a t, a time, you just write a minus and you're happy. And then you check whether the equations are still the same. So that's basically in physics how you check whether it's, we call it time invariant. You basically take this equation, replace all the times going in this direction with times going in this direction, calculate when the same stuff comes out. Obviously, we call it time invariant. It doesn't matter whether you go this direction or this direction. You can do that with many things. That's actually, you can do that with charge, what we call C invariance. You can do it with P as parity, it doesn't matter what it is now. T is like the time, what we want to do. And there is, that has been measured like 12 years ago. Until 12 years ago, we saw that all of physics is time invariant, which it is not. They measured a rare particle decay, which showed that you actually have an error of time. So physics itself, even without the statistical argument, has an error of time, which sucks if you want to do time travel. So physics has an error. The only thing left is what we call CPT invariance. And again, just if you want to have a brag at a physicist party or something, CPT is if you take all the charges, all the directions, and all the times, and put all in front of everything, you put a minus sign, then physics is still the same. Nobody knows why, which is funny. So if you change all three at the same time, physics is still the same. If you change only one, we are screwed. Which is, again, funny, and we don't know why. If anybody has a good idea, it's a sure mobile place. Anyway, and of course, we have all the various paradoxes. We don't go into detail. We can discuss that in the break. We have like the grandfather paradox. If you kill your own grandfather in the past, will you be born, etc. We have like ways around that. We have like multiverses. We have many world theory, time loops, etc., etc., etc. But in the end, most of them don't have causality, which is a problem. So now I told you a lot of problems why time travel doesn't work, which is what we want in the war. So now I tell you how to do it anyway. And again, I'm a theoretical physicist. None of this has been proven somewhere. I mean, only mathematics. The first thing you need to know is the metric. The metric is not to be confused with the matrix. Although the metric is actually a matrix, which is funny, but just as a mathematical symbol. Anyway, so the metric is the physical concept of how do you get as fast as possible from A to B. What do you say? These 2 points, what is the fastest way? Single line, which is wrong.
Zero. It's zero.
It depends. It's not because you have gravity, you have potential. So this might be actually a faster.
Yes.
Or, again, that was a trick question, I'm sorry for that. But even if you go, for example, Heidelberg, if you want to go from A to B, and in a car, for example, a straight line is not the fastest way because there's a house somewhere in the way, usually. So depending where you are, what kind of, we call it the space-time we have, the straight lines might not be the answer. It might be. In a vacuum, straight line is good. In a potential, and potential might be just houses in the way or something, whatever, a field, whatever it is. The straight line might not be the answer. So this is called the metric. The way to mathematically formalize this is called the metric. And this is what you can play around with. Because in the end, in space-time, you want to go from A to B. How do you go there fast? Okay, we need to obviously change that. And there is one thing, or two concepts. The first is the Alcubierre tribe. Might have heard of. It was quite famous like 10 years ago, because this is Alcubierre, the Mexican physicist. He's a good physicist, but he's really famous for his Alcubierre tribe, especially among the Star Trek community, because it's also called the Alcubierre warp tribe. And it works like this. So you have a spaceship, and actually, I'll just show it you in 3D. It's exactly the same, just in 3D. So the blue stuff is the spaceship. Now you say you change the metric. How do you do that? You put a certain amount of energy in front and behind your spaceship. And you need, trust me, a lot of energy. Because you want to contract the space in front of your spaceship, and you want to expand it behind your spaceship. Because what happens then, just physically, and again, this is a theoretical concept, you don't move, but the space around you moves. And that can happen faster than the speed of light, if you have enough energy. I mean, it obviously doesn't work if you have like a bottle of water in front of you. You need a lot of energy. So with that, you can actually move faster than the speed of light. The only problem is the amount of energy you need in front, because you need like a black hole-like amount of energy in front, and you need to have negative energy in the back. Negative mass, which is the problem because so for S5, they don't exist. Again, that might be a problem solved in the future, who knows? There are attempts to actually do that, but so far it does not exist. Mass is actually the only charge, as we call it, which doesn't have a negative equivalent. You have like electrical charge, you have plus and minus, you have color charges, standard and anti-color, and so on. Mass only is positive. Which has different problems, but yeah, that's the way nature is right now. So this, maybe not the best way, but it would work. The other classical example are wormholes. And we have never heard of wormholes. Just to make it very quick. Okay, everybody knows, so I don't give you the... In the end, wormholes are basically just a different metric than the Alcubierre tribe. So what you do is basically, again, take the equations, plug in a different metric, when you have, and the standard, the standard example, does anybody have a piece of paper? Can I borrow that piece of paper for a second? Yes. So, thank you. You want to go from A to B, everybody knows, I guess, the classic example from here to here. It's, I don't want to destroy it. So, yes, you can do that, but that takes a long time. But you also can flip the space-time, and suddenly the points are much closer, and you are faster than the speed of light. So to flip that, again, you need a lot of energy to do it on purpose. If you want to do it on purpose, you have similar problems than this guy. But again, it might happen. I guess everybody has seen Interstellar. Maybe someday at Saturn, one will pop up. Thank you. So, just to wrap it up, space faster than the warp itself, from a physics perspective, faster than light travel, is possible. at least in theoretical physics. And just to say it again, we have never ever observed any of that. And trust me, we've wrong. So far we can do it, but it's a physicist dream, yeah, which might not happen. So thank you for that. Can I just plug one thing because Tom is not here, and we do a podcast together. For the German speakings, you might want to listen to Nerds with double Ö. Here's some QR code if you want to listen to Nerds, the podcast. We also talk about Warhammer. It's not a Warhammer podcast, it's a science podcast, but we talk about Warhammer throughout. So if you're interested, thank you.